Good morning. I am T.Nithyanandam, Assistant Professor in the Department of Mechanical Engineering. Today I would like to cover some topics in the subject of heat and mass transfer. I would like to focus, these are the sub-contents in the heat and mass transfer. Thermodynamics and heat transfer. We need to see the differences between thermodynamics and heat transfer, and we have to see some basic application areas in the heat transfer, and we have to see the historical background about the heat and heat transfer, and we need to see the specific heats of liquids, solids and gaseous, and we have to see basic modes of heat transfer, and we need to see the general heat conduction equation for Cartesian coordinates. Now I would like to take first the differences between the thermodynamics and heat transfer. In thermodynamics is concerned with the amount of heat transfer which is in the form of heat, and there is no indication about how long it will take, the process will take. So in thermodynamics the heat is transferred between two surfaces, between the two mediums, in which there is no indication about the how long, the time is not given in the heat transfer engineering thermodynamics. And thermodynamics simply tells us how much amount of heat is transferred, and it does not give the heat transfer about the modes. The rate at which heat is transferred is not available in thermodynamics. But in heat transfer, heat is the form of energy which can be transferred from one medium into another medium as a result of temperature difference. The study of science which deals with the rate of such energy transfer is called as heat transfer, and the basic requirement for the heat transfer is the temperature difference. Like when the pressure difference which creates the fluid flow, the potential difference which creates the electrical flow, current flow, and the temperature difference is the driving force for heat flow. Now we have to see some important application areas in the area of heat transfer. I would like to give a very good example for the application area. First one is heat exchangers and condensers, boilers, furnaces, evaporators. These are all the very good examples for heat transfer areas. Now I would like to focus one important topic. In the case of thermal power station, we are having a steel tube. Through the steel tube, steam is passing through the steel pipe. Now the temperature of the steam may be 100 degrees Celsius, it may be a saturated steam. Now the water which is passing over the tubes. Now what we have to see as a heat transfer engineer, what should be the temperature at the entry of the tube which may be covered by another tube. The steam is cooled, so what should be the entry temperature of the water, and what may be the expected temperature of the water at the outlet, so that as a heat transfer engineer we have to see the temperature distribution among the length of the tubes. And I would like to give one more example. We have to arrest heat losses in some cases. For those cases we have to identify the length of the tube. So the hot water or the cold water may be flowing through the tube. The steam which is passing over the surfaces, the steam temperature may be 100 degrees Celsius, and the water temperature initially it may be 20 degrees Celsius. The length of the tube will be unknown. Suppose if we want to find out the length of the tube for the particular outlet temperature, so we need to have some calculation. This calculation have to be done by heat transfer engineer, or if we know the length, the output temperature can be also calculated. if you know the output temperature, what should be the length to reach the output temperature, that has to be calculated. These things will be done by heat transfer engineer. These are all the important roles of heat transfer engineer. And next thing is historical background about the heat transfer. Now in 1789, Stefan-Benjamin Thomson, what he told, he proposed caloric theory. In this caloric theory, what he insisted, heat is like a fluid like substance. So the substance, the heat can be poured from one body to another body. So this is the way he defined the heat in the caloric theory. In later 18th century, in 1798, Mr. Thomson, what he invented, heat is generated by friction, by the friction, so that the theory which has been put, it is actually which we are on interest on friction. In later years, in 1843, Mr. James P. Joule, what he invented, heat is not like a fluid, like a substance. So that the theory what they found Mr. Anthony Lavoisier has been put to the rest, which has been abandoned in the later years of 19th century. So finally, the kinetic theory of gases has been introduced. Kinetic theory of gases has been introduced, in which in kinetic theory molecules are tiny balls which are in random motion, which possesses kinetic energy. So finally, heat may be defined as energy associated with the molecules or atoms which are in random motion. So that we can define the heat. Heat is the energy which is random in motion, the molecules having the kinetic energy. And now we will move to the specific heats. So we can denote the specific heat as C. So the amount of energy required to rise the temperature of substance 1 degree by 1 degree for the unit mass of the substance. This is called as specific heat. We can see specific heats at constant pressure and specific heats at constant volume. So at constant pressure, the amount of heat required to raise unit mass of substance by 1 degree. We can say kilojoules, it is the amount of heat required for unit mass of substance to raise the temperature by 1 Kelvin or 1 degree Celsius. This is happened at constant pressure, we can say specific heat at constant pressure. This is happened at constant volume, we can define C, specific heat at constant volume. Now we have to see the specific heat capacity of gases, liquids and solids. Now I would like to focus the specific heat capacity of gases. Now specific heat capacity of gases is depending on temperature. Specific heat capacity of gases is the function of temperature. When the temperature increases, the specific heat capacity will be changed. For example, if you are taking a substance, water, we can increase the temperature from 100 Kelvin to 101 Kelvin. The amount of heat required to raise this temperature for 1 kilogram of substance is 0.718 kilojoules, and when we increase the temperature of the substance from 1000 degree Celsius to 1001 degree Celsius or 1001 Kelvin. So for this temperature difference, we have to supply 0.873 kilojoules amount of heat. So, the specific heat capacity is the function of temperature for gases. Now, I would like to talk about specific heat capacity of the liquids and solids. In the specific, when we are talking about the liquids, the intermolecular force will be higher than the gaseous, so that the specific heat capacities will be identical for liquids and solids. For example, I would like to give specific heat capacity of the solid for iron. I can take example for iron. For this material, for this metal, the specific heat capacity at constant pressure, specific heat capacity at constant volume will be identical. Value will be 0.45 kilojoules per kilogram Kelvin. So, this is the solid specific heat capacity, and I would like to talk about water. Water is having the specific heat capacity Cp equal to Cv equal to 4.186 kilojoules per kilogram Kelvin. So, this is for air, gases, and this is for water, liquids, and this is for solids, iron. So, these are all the changes of specific heat capacity depending on the temperature. So, the changes will be happening in gases and the changes will not be happening in solids and liquids. Now, I would like to talk about the modes of heat transfer. Basically, there are three modes of heat transfer. We know well, first one is conduction, second mode of heat transfer is convection, and third mode will be radiation. Now, I would like to talk about conduction first. In conduction heat transfer, the heat is transferred from higher energy molecules to the lower energy molecules as the result of temperature difference. So, the heat is transferred from the higher energy molecules to the lower energy molecules as a result of temperature difference. For heat transfer, there should be a temperature difference exist. So, if the temperature difference is not exist, that means the system which should be in thermal equilibrium, there should not be heat transfer. So, that in conduction heat transfer, stop. சும்மா லாக் பண்ணி விட்டுருப்பாங்க. In the three modes of heat transfer, now I would like to focus on conduction heat transfer. In conduction heat transfer, the heat is transferred from higher energy molecules to the lower energy molecules in the same substance. So, the conduction heat transfer will take place in solids, liquids and in gaseous form. So, that now I would like to define the law which will be behind the conduction heat transfer is called as Fourier's law. So, in Fourier's law, heat is directly proportional to the rate of heat transfer is directly proportional to the surface which is normal to the heat transfer and temperature difference and inversely proportional to the thickness of the layer. Now, rate of heat transfer is directly proportional to the surface area, the area which is normal to the heat flow, and temperature difference and inversely proportional to the thickness of layer. Now, I will remove the proportional by introducing an constant of proportionality. Q will be equal to K into dt divided by dx. Here I have to put negative sign, the negative sign which indicates heat flow in the positive x direction. Heat is always flows from higher temperature side to the lower temperature side. So, that heat negative sign which indicates that heat flow will be in the positive x direction. So that now I would like to derive the unit of thermal conductivity. The constant proportionality is called as thermal conductivity. We can define thermal conductivity. Thermal conductivity, it is ability of the material to conduct the heat. It is the material property. Now K is equal to Q into dx divided by dt. I can define the unit. Q is in watts, rate of heat transfer is in watts, divided by temperature is in dt, and K is equal to Q dot into dx and dt. So here I can define the unit of thermal conductivity is Q dot is equal to watts per meter Kelvin. This is the unit of thermal conductivity. And now thermal conductivity of different materials. I would like to talk about the thermal conductivity of different materials. Now Q is equal to AS. Here I can define into AS. Q is in watts, dx is in meter, and dt is in Kelvin and meter square. So I can cancel, we will get watt per meter Kelvin. Now I have to give some values of thermal conductivity for different materials. So the maximum thermal conductivity material is diamond, 2300 watts per meter Kelvin, and lower thermal conductivity substance is air. For air, thermal conductivity is 0.026 watt per meter Kelvin. In between aluminum, bronze, brass, copper and wood, these are all the materials having thermal conductivity between 0.026 to 2300. For example, we can say we are regularly using gold. For gold is having thermal conductivity is 317 watt per meter Kelvin. So this is the thermal conductivity value for gold. Now variation of thermal conductivity with respect to temperature that we have to see. Now we can see the variation of thermal conductivity for gases. When we talk about the gases, when we increase the temperature of the gases, the thermal conductivity of the gases will be increasing. So that the thermal conductivity of the gases will be increasing when we are increasing the temperature. But for solids, when we increase the temperature of the solid, thermal conductivity of the solids like aluminum, copper will decrease. So this is the effect of temperature on thermal conductivity of liquids, gaseous and solids. Now we will move to the convection heat transfer. Convection heat transfer, it is the amount of rate of heat transfer between solid surface and the fluid which is in motion. So that here in convection heat transfer, the heat is transferred from the higher energy particle which is in solid to the adjacent layer of the liquid. So this heat transfer is by conduction. Then if the fluid which is in motion, the heat is transferred by conduction and fluid motion, it is called as convection. So both the mode of heat transfer will be occur, conduction and fluid motion combinedly called as convection. In convection heat transfer, I would like to draw a temperature profile and velocity profile. In this mode of heat transfer, so this is the velocity profile. The fluid velocity on the surface will be 0 and the fluid velocity when it is towards the top of the fluid layer, it will increases and it reaches the maximum velocity. It is called as free stream velocity, and the thickness of this layer is called as hydrodynamic boundary layer. Now when we see the temperature distribution along the plate, so in this case the temperature on the surface of the fluid will be very high. When it goes towards top, the temperature will be gradually decreased to reach the minimum temperature, that is called as free stream temperature. The thickness of this layer is called as thermal boundary layer. Now, we have to see the convection heat transfer coefficient. Before that, we need to talk about the law behind the convection heat transfer. The law is called as Newton's law of cooling, which represents H into AS into delta T. Delta T is nothing but TW minus T infinite. Here H is the convection heat transfer coefficient, AS is the surface area, and TW is the surface temperature, and T infinite is the fluid temperature. Now, I can say the value of H. So, number of experiments have been conducted. From the experimental parameter, we can say the value of convection heat transfer coefficient lies for gases in free convection. For gases in free convection, the value will lie between 2 to 25 watt per meter square Kelvin. Here we can see there are two different types of convection heat transfer occur. In this convection heat transfer, first one is free convection and the second one will be the forced convection. If the fluid flow will be happened by buoyancy forces, there is no flow of external medium like fan or blower. Heat is transferred from the solid surface to the fluid. The motion of the fluid is created by the buoyancy forces. Buoyancy forces is nothing but which is due to the density difference, so that the free convection will be happening. If we are using any external medium for creating the motion of the fluid, so this kind of convection is called as forced convection. For free convection, the heat transfer coefficient for the free convection of gases will be 2 to 25 watt per meter squared Kelvin. Here I have given the unit watt per meter squared Kelvin. We have to derive the unit for watt per meter squared Kelvin with the help of this law. Now, Q is equal to H into A into delta T. Now, H will be equal to Q divided by A into delta T. The unit for Q is watts and area is meter square and temperature difference will be Kelvin. Now, H equal to watt per meter square Kelvin. This is the unit for convection heat transfer coefficient. Now, for free convection, the convection heat transfer coefficient will be 2 to 25 watt per meter square Kelvin for gases, and for free convection of liquids 25 to 1000 watt 250, 25 to 250 watt per meter square Kelvin for liquids. For boiling and condensation, that is called as phase change heat transfer, the convection heat transfer coefficient value will lie between 10,000 to 1 lakh watt per meter squared Kelvin. This is the maximum amount of heat can be transferred by using convection heat transfer. And now we have to talk about next mode of heat transfer is called radiation. In the radiation mode of heat transfer, heat is transferred by the emission of radiation from a surface. So, the amount of energy transferred from the surface due to its emission characteristics, that is called as by electromagnetic phenomena. Electromagnetic waves will be used to transfer the heat from the surface. So, there is no intervening medium is required for heat transfer. Air is not required or any medium is not required if the heat is transferred, including in vacuum also. Now, the law behind the radiation heat transfer is Stefan-Boltzmann Law, in which Q will be equal to sigma into A into temperature power 4. This is for black surface, temperature of the surface and the surface area, and we are using Stefan-Boltzmann constant. So, the value of Stefan-Boltzmann constant will be 5.67 into 10 power minus 8 watt per meter squared Kelvin power 4. So, this is the value of Stefan-Boltzmann constant. Now, I can derive the unit of sigma for here. We can see Q is equal to sigma into A into Ts power 4. Now, we need the unit of sigma, sigma equal to Q divided by A into Ts power 4. Q is in watts and area is in meter square and the temperature will be in Kelvin power 4, watt per meter square Kelvin power 4. This is the unit of Stefan-Boltzmann constant. Now, we will move to the last content in this topic is general heat conduction equation. So, now for this general heat conduction equation, I have taken Cartesian coordinates to derive this equation. So, now I can draw a diagram for this Cartesian coordinate. So, this is positive x direction, here I can say so this is the point, this is the positive x direction and this is positive y direction and this is positive z direction. In this Cartesian coordinate I can say this point is A, B, C, D and E, F, G and H. This is a element which will be taken from a cubical element, a small element that I have taken for this purpose. So, here for this phase A, E, H, D phase, the heat conducted into the element will be Qx. Now, in the opposite phase, the heat conducted out from the element is Qx plus dx, and in the positive z direction the heat conducted into the element is Quz, and for the positive z direction heat conducted out from the element is Qz plus dz, and in y direction heat conducted into the element will be in the positive y direction, that is Qy, and will be in the opposite direction Qy plus dy. So, for this Cartesian coordinate we have to see, we have to create the energy balance equation for this coordinate. Now, I will write the energy balance equation by first law of thermodynamics. So, total heat conducted into the element Qx, I can write from here Qx plus Qy plus Qz. These three elements are heat conducted into the element plus, here we have to see the energy generated by the element, we have to consider the energy generated within the element. See, it is Q dot, energy generated into the element, which is in watts per meter cube. For 1 meter cube, the amount of heat energy generated by the element Q dot. The energy generation may be in the following forms. It may be in the form of nuclear energy, or it may be in the form of electrical energy, or it may be in the form of chemical energy. Now, in the right hand side, we have to balance the equation. Heat conducted out from the elements are Q x plus dx plus Q x y plus dy plus Q z plus dz, and by first law of thermodynamics, the net heat conducted into the element will be Qx plus Qy plus Qz minus Qx plus dx plus Qy plus dy and Qz plus minus Qz plus dz equal to change in internal energy. How much amount of energy can be stored? So, this changes, rate of change of internal energy can be considered, which is dE with respect to time. So, all these Q's are, we can say it is Q dot, rate of heat transfer. So, here rate of change of internal energy I can represent here as dE by dt. Now, I have to find out all the values from this equation that I have to substitute, we will get the final general heat conduction equation. Now, I have to write the first equation for Qx. So, for finding Qx, we need to have Fourier law of heat conduction. So, in Fourier law of heat conduction, by Fourier law of heat conduction, Qx is minus k into A into dt divided by dx. Here the area, surface area that we have to consider, for this is the Cartesian coordinate, this is dy and this is dx and this will be dz. So, for Qx I have to calculate the area of this surface dy and dz. I can say area will be equal to minus k into dy into dz into dt divided by dx. Now, I have to write for all these directions that we have to consider the equation, so that for one direction means that we can go for an ordinary differential equation, for 3-dimensional equation that we have to go for partial differential equation. So, Qx will be equal to minus k into dy into dz into dou t divided by dou x. So, this is the heat conduction equation for heat conducted into the element in the x direction. Likewise, I have to write the value of Qy and Qz. So, minus k into the area, surface area for y direction will be dx into dz into dou t divided by dou y, and for Qz direction minus k into dx into dy into dou t divided by dou z. These are all the amount of heat conducted into the element. Now, we will move to heat generated within the element, Q dot. Q dot will be equal to amount of heat generated into the element per meter cube is Q dot. We are having the volume of dx into dy and dz. Now, Q dot into dx into dy into dz. This is the amount of heat generated into the element which is in the volume phenomena. Now, I have to write the equation for Qx plus dx. What is Qx plus dx? Amount of heat conducted out from the element is Qx plus dx in the direction of x axis. Now, for this equation I can write Qx plus dou by dou x into Qx into dx. So, this is the form of heat conducted out from the element can be written in the x direction. So, plus I can write plus this equation have been written. Now, we have to see the one dimensional heat conduction equation for a plane wall. So, the temperature at the left end of the wall is T1 which is at higher temperature, and right end of the wall is T2 which is at the lower temperature. Heat is transferred or conducted into the element from higher temperature side to the lower temperature side. The surface area of the layer is A and the thickness of the layer is L. The right end is x1 and the left end will be x2. Now, from one dimensional heat conduction equation we know well dou square T divided by dou x squared will be equal to 0. Here we have to assume there is no unsteady state, the heat transfer will be steady state, there is no heat generated within the element, so that I can write dou square T divided by dou x squared will be equal to 0. For this I have to integrate this equation, dou square T divided by dou T divided by dou x will be equal to C1, and again I have to integrate T will be equal to C1x plus C2. This is the general form of equation for a plane wall. If I apply this equation at the left end, I can get T1 will be equal to C1 x1 plus C2. I have to apply this equation at the right end. T2, temperature at the right end will be T2, and I can introduce C1 into the value of distance is at x2 plus C2. This equation is called as A. I can put this equation as B. Now, the equation A minus B implies A minus B will be equal to T1 minus T2 equal to C1 minus C2 into x1 minus x2 into C1. So, C2 will be eliminated, and from this equation I can write C1 is equal to T1 minus T2 divided by x1 minus x2. So, this is the constant C1. Next, I have to use the equation A. I have to substitute the value of C1 in the equation A. I will get C2. Now, T1 is equal to, what is C1? T1 minus T2 divided by x1 minus x2. This is C1 into x1 plus C2. So, from this equation I can say C2 will be equal to T1 into C1 value will be T1 minus into x1. Now, x1 minus x2 divided by T1 minus T1 minus T2. So, C2 will be equal to into divided by x1. Now, I have to substitute all the values in this general equation. We will get the temperature distribution, that is x minus T minus T1 divided by T1 minus T2 will be equal to x1 minus x divided by x1 minus x2. With the help of this equation is called as temperature distributions. If you want to find out the temperature at any point between x1 and x2, we can get the value of temperature, or if we want to know the distance at two different temperature, we will get the x value. So, this is the temperature distribution equation from this one dimensional layer. And now, we know well dt divided by dx. We know the heat transfer by conduction is governing the law minus k into A into dt by dx. I can say q equal to minus k into A into dt is the temperature difference, that is T1 minus T2 minus T1 divided by dx is the thickness of the layer, that is x2 minus x1. Now, I can say q is equal to k into A into, I can write T1 minus T2, the minus sign will be eliminated, divided by x2 minus x1. x2 minus x1 is nothing but k into A into T1 minus T2, which we can write L, thickness of the layer. So, that q equal to T1 minus T2 divided by L divided by Ka. This term is called as thermal resistances. So, we can compare this equation with the electrical equation, that is V I equal to current flow, I is equal to V divided by R. So, current flow for driving force is the potential difference. So, that I can compare this equation. For heat flow I can compare with the current flow, temperature difference I can compare with the potential difference, and L by Ka, the term is called as resistance. Here it is called as electrical resistance, but in heat flow we can call this as thermal resistances. Q thermal resistance equal to L divided by K into A. And now, if I am going to write this equation for a composite wall, the wall made up of 3 different layers, and we have to include the convection heat transfer at both the ends. I can write the one dimensional heat conduction equation. So, here Q is equal to, I can draw the diagram for composite wall, 3 different layers, 1, 2, 3, which is having different thermal conductivity, and thickness of this layer will be L1, L2 and L3. Heat conducted the element, heat transferred into the element will be Q, and now I have to write the equation for this, and also I have to include convection heat transfer in the both the sides. Here convection heat transfer coefficient in the right hand side will be HB and the left hand side will be HA, and the temperature at this end, fluid temperature at this end TB and this end will be TA. Now, the temperature at the interfaces, this temperature will be T1, next temperature between the layer, first layer and second layer will be T2, between second layer and the third layer will be T3, at the end of the final layer the surface temperature will be T4. So, I have tried the equation for this composite layer of 3 different materials. Heat transfer, rate of heat transfer is equal to total temperature difference, that is called as TA minus TB divided by total thermal resistances. Here we can see 5 different thermal resistances for convection resistance, and for this material conduction resistance, and for these 2 materials are conduction resistances, and for this outside convection will be convection resistances. So, Q will be equal to TA minus TB divided by convection resistance 1 divided by HA into A in the left hand side, plus L1 by K1A is the conduction resistance, plus L2 by K2A is the conduction resistance for the second layer, and L3 by K3A is the conduction resistance for the third layer. Finally, 1 divided by HB into A. This is for convection resistance at the outside layer. So, this is the heat conduction equation for composite layer which is having convection at both the ends. So, this equation will help us in numerous way to solve very big problems in the heat transfer. So, up to now we have seen the basic mode of heat transfer, specific heats, historical background, we have seen application areas and mode of heat transfer, and finally we have derived general heat conduction equation. Thank you.